Hey guys, in this video I wanted to take a couple of minutes to explain to you the different phases of what's called the cardiac myocyte depolarization-repolarization cycle. So this is basically an action potential, but for cardiac muscle cells. It's worth noting here that this action potential for your cardiac myocytes is different from, say, the action potential of a cardiac conductive cell or a nerve cell like we talked about in exercise physiology. So what I'm going to talk about here is specific for cardiac myocytes. So to start us off, I wanted to introduce you to phase 4. So phase 4 represents the resting membrane potential. And you should know that when a cardiac myocyte is at rest, the concentration of sodium tends to be high on the outside of the cell, and sodium channels are closed, so sodium isn't able to sneak into the cell. Concentration of calcium is also high on the outside of the cell, and the concentration of potassium is high on the inside of the cell. You may also hear that there's a little bit of potassium leaking out of the cell during phase 4 through, I guess, what we would call leaky channels, but we won't worry about that too terribly much, but you should note that it does occur. During phase 4, we also have the sodium-potassium pump, which is maintaining and restoring sodium on the outside of the cell, potassium on the inside of the cell, and helping to keep that membrane potential at its normal negative level. So when a cardiac myocyte ends up getting stimulated, the heart will transition, or that cell specifically, will transition into what's called phase 0. So in phase 0, we have sodium rushing into the cell very, very quickly. We also have calcium starting to come into the cell, but it's coming in more slowly. This travel of ions into the cell creates this very, very fast depolarization. So you see on the figure, we have a sharp upward trend of our membrane potential. At the end of phase 0, or at the end of depolarization, sodium will stop coming in, and that brings us into what's called phase 1. And when that happens, we start to see the membrane potential come down relatively rapidly for a short period of time. And so this phase 1 is what we call the early rapid repolarization phase. After phase 1, we enter into phase 2. What's happening during phase 2 is the membrane potential is coming down, but it's coming down more slowly. And the reason that it's coming down very slowly is that we still have calcium coming into the cell, but at the same time we have potassium moving out of the cell. And so the charges of calcium coming in are being balanced by the potassiums that are leaving, and that's helping to maintain almost a plateau. Not a true plateau, but it's representing sort of like a plateau here in phase 2. Basically what we see is that the membrane potential is held in the positive range for longer than we see in a traditional action potential from, say, a nerve cell. At the end of phase 2, we see the calcium start to stop coming into the cell because calcium channels have closed, but we still see potassium leaving the cell. So as potassium leaves the cell, it's bringing those positive charges with it, pulling the membrane potential back down into the negative range. So we see another essentially rapid phase of repolarization. And so this is the late rapid phase of repolarization in phase 3. At the end of phase 3, we end up in phase 4 again. So during phase 4, we have the sodium-potassium pump trying to restore those sodiums back on the outside of the cell, trying to restore the potassiums, back on the inside of the cell. And that's also going to help keep the membrane potential in the negative region. So the reason that the cardiac myocyte action potential is really interesting is because this plateau that we see during phase 2, which is basically a period of slow depolarization, helps to keep the cell in what's called a refractory period for a longer period of time. So a refractory period just means that it's harder to get the cell to be activated. And in fact, during phase 1, phase 2, and the beginning part of phase 3, we are in what we call an absolute refractory period. So during this absolute refractory period, no matter what type of signal comes in, no matter how strong it is, the cardiac myocyte will not be able to depolarize again. And so this is important because this absolute refractory period, or this extended period of repolarization, is going to force the electrical activity to travel in a very specific direction. And this enables the contraction of the cell to also follow a very specific path. So the depolarization of a muscle cell is what causes contraction of the muscle cell. And if you can control the direction the depolarization wave travels in the heart, you can control the direction the contraction occurs in the heart. So at the end of phase 3, we transition into what's called the relative refractory period. So during the relative refractory period, which takes place during all of phase 4 and the very tail end of phase 3, you can get the cardiac myocyte to be activated again. It just takes a strong stimulus. And so that's kind of the gist of what you should know for the action potential of a cardiac myocyte.